Hi everyone, thank you Tom for the introduction and thank you all for being here today. I'm very happy to be here. So I think my presentation is going to shift gears a little bit. We've been having a lot of talks about uncertainty and how we try to measure risk and understand how much uncertainty we have in our systems and in all of our assessment. And my talk is going to go a little bit kind of deeper into the underlying structural engineering aspect. I'm just going to talk more about, hopefully give you an idea of some of the new directions that we have in structural engineering modeling of structures, specifically reinforced concrete. So before I begin, I'd like to acknowledge my current supervisor, Dr. David McCallan at University of Nevada, Reno. And the first part of my presentation is going to be about some of the work that I'm doing as a postdoc at UNR under this very big project funded by the Department of Energy, exascale computing effort. And then in the second half of my presentation, I'll talk about extensions of some of my doctoral work when I was at UC Davis. So over the past few decades, most of the work of the structural engineering community has been geared toward improving the ways and our certainty in predicting extreme limit states in structures, particularly when we're looking at earthquake engineering, because we want to both assess the safety of our structures and also incrementally improve our building code provisions. And there are key big challenges that stand in the way of that, and most of the efforts have been working on them. Mainly, our models have a lot of limitations. So all of our structural analysis models are limited. And these limitations come from, among other aspects, the sparsity of observations. So we always have limited observations in tricky areas, like understanding the variability in earthquake ground motions, or understanding how structures perform near collapse. So this has been a big challenge for a lot of the work done in this area. So I think I really like this plot. It's from a study done in Stanford in 2005. Talks about how much uncertainty we have when we're trying to assess the collapse of a particular system. And what we're looking at here tells us that the very large chunk of the uncertainty comes from the ground motions, what we call the record-to-record variability. So this is an attribute of the ground motion itself, and it's better understood and studied when we're looking at the regional scale, the variability at the regional scale. And this is what I'll talk about in the first half of the presentation. The other contributors to uncertainty are aspects of the structural model itself. Most notably here, the post-capping stiffness, which is something I'll come back to in the second half of the presentation. So these are attributes of our structural models themselves, and they're better understood and improved when we zoom in and talk about our modeling at the material and component scales. And this is where I'll talk about in the second half of the presentation. So when we're looking at the regional scale, there's been tremendous effort as part of the Department of Energy exascale computing projects in developing three-dimensional physics-based ground motion simulations. And Dr. Abrahamson this morning talked about the shift toward using more and more of these three-dimensional ground motion models. And so as part of the structural engineering team, my interest was taking these ground motions and then try to develop an understanding of how we see variability in risk to reinforced concrete structures when we're looking across the entire region. The way that works is that we have kind of a large domain. In this particular case, you're looking at a 40 by 100 kilometer domain with the fault that ruptures, and then the fancy simulations on the SW4 code gives you thousands and thousands of ground motions at grip points, and then I apply these to reinforced concrete structures and see how we see variability in risk. And the result of that is what we call structural risk maps. So these are maps that tell us something about the risk. In this case, we're looking at the particular maximum interstory drift structural demand that structural engineers use to measure risk in a lot of cases. And the color coding here corresponds to different levels. And So what we're seeing here, what we're seeing from these simulations is that we have very large variability in the risk to structures, particularly very near the fault rupture. This is for a magnitude 7 fault rupture in this particular case. To give you an idea of how big that is, if you go horizontal line along the fault, your maximum inter-story drift demand changes, it varies by a factor of 8. So this is a very large variability, and it really raises a lot of questions about how engineers can take that into account in our design provisions for structures near active earthquake faults. And then we kind of try to zoom in and see what the variability that we see in the near fault, well, 10 kilometers from the fault, versus if you go further than that. And you can really start to see the very large variability and the higher structural demands. So on the left here, we're looking at what happens within 10 kilometers of the fault, and you see very large structural demands and relatively large variability, whereas on the right, everything kind of goes down when you're more than 10 kilometers away from the fault. And so really the challenges for engineers is how do we quantify this and incorporate that in our analysis and designs. Another area of interest that we're starting to look into is studying the long sought after forward rupture directivity effects that people are really interested in looking into in the community. There's been a lot of interest in that. We want to know how typically when structures are in the path of the rupture of the fault, we get ground motions with very large velocity pulses, and these affect the structural demands very, very significantly. So we're starting to look into that and see more and more about how we can quantify the effects of that to structures. And here we're looking at the ground motions that we see in this particular case with large velocity pulses. And you can start to zoom in and see that structures that are in stations where you have these large velocity pulses and what you would call the directivity effects, they have much higher structural demands than structures that are not in the rupture path. And I think we get a lot of valuable relative insight when we're comparing different demands at different stations. And this is a very important question. But another equally important question is, in absolute sense, can we really judge, can we talk about how well the building is doing in these, is subjected to these pulse-like ground motions or the very large ground motions that we see here. And a previous speaker, Brian Strong, talked about identifying vulnerability of non-ductile concrete buildings to collapse, and this is kind of a big issue. How do we identify that? And to do that, I think we really have to kind of zoom in a little bit more into how we're actually modeling the underlying buildings in these simulations. And again, it really comes down to how accurate your model is. In this particular case, I'm using one of the common methods that people use for modeling buildings in collapse assessment, where you kind of lump your nonlinearities. Certain areas of your model you expect to have nonlinear response. And it all really comes down to how accurate your constitutive relationship is, your underlying relationship, right? Especially when we start to get, this isn't a very ductile structure. You can start to see that when you kind of reach this post-capping zone, things become really tricky, right? Because you want to know at this area, do you lose 10% capacity of this component, or is it 30%? And this will tell you how well your building is going to do underneath all of this. And I kind of loop back here to the plot that I started with. I really like this plot. So the post-capping stiffness was actually found to always be one of the largest contributors of the system parameters, of your model parameters, to the variability in collapse, meaning that it really comes down to how you model this area, this part of your model, to be able to tell if your building, how vulnerable your building would be to collapse and how much significant damage you would see, if any. So then it becomes natural to ask the question, okay, well, how accurate are the underlying models? And always we want to answer that question, we have to get back to observations that we have. and there aren't that many. So we work with what we have. And when we compare the underlying models to the experiments that we have, we saw two things. That these models are conservative, and because there are no observations, and we don't like that very much because it doesn't give us an accurate estimation of the uncertainty. And that the bigger conclusion is that there is still very large uncertainty, and that we need to improve our models to be able to talk more and more about the strength degradation structural members that will then help us identify vulnerability to collapse in buildings, reinforced concrete specifically. And I can kind of talk about this for a long time, but I'm not going to. But structural engineers in the room will know that, we usually use certain idealizations for our structural modeling of buildings or bridges. And these usually fall into one of these categories. They all have their problems, they all have their idealizations. But a lot of the work in the community in the past, I would say, couple of decades have been on improving this type of model. It's called the distributed plasticity fiber section model. People have been trying to improve the ways this model simulates strength degradation because it is extremely deficient, so that we can use this type of model to better understand the strength degradation and deterioration of our models, which will kind of lead us all the way to understanding collapse and then understanding stability of damage and recovery, and all of that on kind of bigger and bigger scales. So this is where I did a lot of my work as a doctoral student. And like I said, there's been a lot of work in the community to kind of improve this type of model. It has a very inherent problem, difficulty with the models that your answer depends on the characteristic length of your finite element model. So it gives you an unphysical response when you're talking about strength degradation. And this is a very big issue that the community has been working toward fixing. So what I'll try to focus on here is the third type of model that people have been kind of, over the past 10 years, have kind of started working on this idea as a fix to the type of distributed plasticity models that we use for structural simulations. And this isn't very common. You may not have heard of it at all as a structural engineer or even a structural engineering researcher. And the reason is this type of models kind of changes the paradigm a little bit of how we do our structural modeling. And in some way, it actually changes the paradigm of the finite element analysis altogether. So it's it kind of changes the way we do our modeling, but it overcomes a lot of the difficulties that we face with our current structural analysis models. And all of these, I listed here some of the examples of these models in literature, and they all kind of are built on the same simple premise, I would say, of conducting some form of spatial averaging in your finite element analysis model. And then they all differ in how this averaging is conducted and how to define the domain in your model where you do the spatial averaging. They're all kind of small details, but in general, they're all based on the same idea. And for the particular case of the model that I worked on, we kind of get some information from the scale of the concrete material itself that tell us something about how the damage is going to happen in a structural member. And in that way, we kind of get a sense of, we average out the damage in a way that tell us macroscopically on the scale of your component or your building how the building how the component will perform and what the rate of the strength degradation is. And we want it to be in a way that is also easy to generalize to different problems. So I'm going to show some results from using this type of non-local model. Here we're looking at your traditional simulations using the fiber section model the structural engineers like to use in simulating a quasi-static response of a column. And then here we're looking at the response with this type of non-local model, which overcomes the big mesh sensitivity problem of the conventional models. And then we're also sometimes, a lot of the time, interested in looking at strain distributions, curvature demands in the members because it tells us something about, again, the damage and how much ductility do we have. And so we're better off capturing these with a model that overcomes all the issues, the mesh sensitivity issues that we see here. Here we're seeing the modeling using different sizes of mesh gives us different answers, whereas the non-local model overcomes that problem. And again, if we want to make conclusions about how well this type of model is working, we have to go back to experiments. And again, we don't have a lot of them, but if we kind of go back and start to compare the performance of the model to experiments, we see that in general it is doing very well. So it has more promise in kind of increasing our ability to be able to capture strength degradation in general. And finally, the question that kind of started all of this, would we have a difference, a significant difference, if we use this type of model to predict collapse of reinforced concrete buildings? We started by looking at single columns, and we tried to assess the collapse using the traditional methods that structural engineers use, doing incremental dynamic analysis and so on. And so here you're looking at fragility curves for a column. And yes, the answer is we do sometimes see a significant difference in how we're predicting in the median collapse capacity and how we're predicting collapse for even single columns. So this tells us that our current models, they need to be shifted in a way where we can overcome the problems, because the difference can be significant in assessing our collapse capacities. Then other interesting questions were, to me, that how do we see difference in predicting collapse between different types of models, different alternatives that are used in the community? And I think it was also shocking that we see a very large difference between using a distributed plasticity model and a lump plasticity model or concentrated plasticity model. So in certain cases, you can see a lot of difference. And arguably, these are two types of models that provide you with the right answer as a structural engineer. And so I think what that really says is that even though we sometimes have some indication of how each model is performing, because we have experiments that we can compare to in a simplified loading scenario, we usually, most of the time, we don't have the answer. And so I think most of the effort of the structural engineering community over the past few years, and some of the efforts that I've been working on, have been not only to improve the way that we're modeling the strength degradation, assessing collapse, but also in understanding and quantifying how much uncertainty do we have when we're using alternative types of models. With that, I'll sum up. The theme of my presentation has been about how there is so much uncertainty when we're designing structure to resist earthquake loading. And that comes from both understanding of the earthquake loading itself and then a simulation of the resistance of the structure and the nonlinear complicated response of the structure to ground motions. On the side of the ground motions, we think that having these three-dimensional generated ground motions and are based on physics models will help us tremendously in understanding the variability of risk over entire regions, and that will help us improve our building code provisions for structures in the near fault area. Now, on the side of the simulating the structural resistance, things are still complicated. We know now that to assess collapse, we need better and better models that can capture strength deterioration very accurately, and that I think the school of the non-local modeling approach kind of get us a little bit closer to that, but there are still a lot of other modes of deterioration that we need to incorporate to be able to use those to more generally assess collapse of reinforced concrete structures. Thank you very much.